Hi, this is Dr. Gulshan S, and this question is on the Broglie wavelength. A particle of mass 4.1 10 to the power negative 28 kilogram starting from rest experiences an acceleration of 2.4 10 to the power 7 meter per second square for 5 seconds. What is its de Broglie wavelength lambda at the end of this time? So this question is based on de Broglie wavelength. De Broglie wavelength is a wavelength associated with moving particles. Now here, in order to have this wavelength significant, the mass of the particle has to be very small and it should be moving. The reason for this is that Planck's constant is 6.62 10 to the power negative 34. So if this quantity is very small, this 10 to the power negative 34 is very, very small quantity. And therefore, this quantity has to be significant in order to make this as significant value. So the mass of this particle has to be small and it should be moving to have a reasonable de Broglie wavelength. Now, what is this reasonable value? You cannot have this particle as say 10 kilograms or 50 kilograms because the mass is too big. The wavelength cannot be detected by any instrument. So in this particular case, the mass of the particle is really very small. It is 4.1 10 to the power negative 28 kilograms, which is almost mass of a proton. So subatomic particles like protons, neutrons, and electrons, if they are moving with significant velocity, then only they will have a detectable or significant wavelength. Now in this particular case, final velocity minus initial velocity is equal to acceleration times t, that is time for which it is being accelerated. So the final velocity is 2.54 multiplied by 7 multiplied by 5 makes us 1.2 into 10 to the power 8 meter per second. So this is a fairly large velocity with which this particle is moving, and this mass is very, very small. It's just 4.1 10 to the power negative 28 kilogram. So if I plug in all these values into this equation, lambda is equal to h upon momentum, mass into velocity, I'll get 6.62 10 to the power negative 34 divided by 4.1 10 to the power negative 28, which is mass, and the velocity, which on acceleration has become 1.2 10 to the power 8 meter per second. If I plug in these values, I'll get the value of wavelength associated with this particle to be 1.35 approximately into 10 to the power negative 14 meters. I've taken significant figure as 1.35, whereas the actual value works out to 1.345. So if we round off to the second decimal place, and this is important because the 10 to the power negative 14 is a very, very small quantity. So once again, this de Broglie wavelength is significant because the mass of the particle is very small. You cannot have a significant wavelength associated with a moving car because its mass will be too small, and because of this Planck's constant being of the order of 10 to the power negative 34, if this value is large, the wavelength will become too small. So this wavelength 10 to the power minus 14 meters can be detected by some instruments which are sensitive to detect de Broglie wavelength. That's it. Thank you.